Hi everyone, I'm Joe Payne and this is Nathan Kong, and we're from the Robomechanics lab at Carnegie Mellon, and we're presenting on Flamingo Bot, which is a zero-energy standing bipedal robot. So sort of the motivation why we wanted to make this is we saw this awesome paper from Chang and his collaborators on the passive stability properties of flamingos. And sort of before we get into that, I'm just going to go over a little bit of the terminology that we use going forward. So the Tmp joint is the lowest joint in the flamingo's body. It sort of connects its foot to, it's the lowest joint, and it's sort of, in a human, it's equivalent to a toe joint. And then their ankle joint is what you would think of as a human's knee joint. And then knee and hip are both up under the feathers of the flamingo in the body. So basically all the joints are just shifted one up from a human as if they were standing on their tiptoes. So some of the research that Chang did is looking at a sleeping flamingo on a force sensor and looking at the center of pressure over in different behaviors. So as it's active and goes to trying to become stable and then finally falls asleep, the center of pressure becomes more and more stable directly under the Tmp joint and starts to move around less and less, which sort of shows that it's not so much an active property as a passive one because the flamingo is falling asleep while this is happening. They also performed experiments on Flamingo Cadavers. Here they've fixed it above the ankle joint, which they can do because in a flamingo, when it stands on one leg, it sort of locks out because of that leaning position. And you can sort of see how it returns to center as they displace it within this pose. So we thought that this was like a really interesting thing that we could use for a robot. And we were looking at like where do we still need this? And so bipedal robots are really awesome. They can go over rough terrain, they do all of these awesome things, but they still use a lot of energy when they're just standing still. So for example, Cassie draws 100 watts when it's just standing still, and Atreus actually can't stand still. It has to walk in place to remain upright. And we think that this is sort of an area where we can still improve by looking at these properties from the flamingo. So sort of the motivation for this is there's been research showing that in search and rescue applications, over 50% of the time, the robots are just standing still. And so if we can improve that efficiency, then the robots can spend more time in the field doing what they're supposed to be doing and less time going back to get charged and all of that sort of stuff. So there's actually been prior work done optimizing existing robots. Here you can see Rex sort of leaning forward and backward, trying to minimize the energy, the active energy it's putting into its motors to remain standing upright. But we still think that there's motivation for taking that number from a minimal within an existing robot to 0 within a robot specifically designed for this. So we used all these things, these really cool properties that we found in flamingos in order to create the Flamingo Bot, which you can see here on the right, and it sort of uses the same mass distribution and hard stop properties that we saw in real flamingos. The mass is sort of slightly in front of the knee, and it uses the same hard stops. And sort of just looking at it, it seems like it's pretty trivial that it's standing there stably, but like a flamingo, it's pretty top heavy, and the legs are pretty lightweight, and it's actually very easy that it just collapses on its own when it's not in this specific standing position. Now I'm going to let Nathan tell you a little bit more about the design of the Flamingo Bot.
Yeah, so like what Joe was saying about how the mass distribution is more on its front, this allows the center of mass to apply a moment on its hip and knee joint to let it hit into this knee hard stop in the top left, as well as hitting a Tmp hard stop, which is on the bottom left here. But this moment actually hits the ankle hard stop off of its ankle, and that's why we use the spring over here to kind of pull it back into that hard stop. And this is similar to a flamingo where they have tendons that kind of act like a spring to provide like a mechanism that drives it into its hard stops. One important thing to note with this knee hard stop over here, it's actually both a knee and a hip hard stop, and it's not only constraining just one of the joints at a single moment. It's actually the combination of the two. So when it's in its walking regime, we can actually let it pop off of this hard stop, and it usually doesn't interfere with walking behaviors. One other important thing is, or one difference is, a flamingo stands on one leg. Our robot stands on two. And this helps it with stabilizing itself on the frontal plane, while a flamingo actually has some difficulty with that. One metric we looked into for determining stability is hitting it with a mass on a string. And this allowed us to measure different impulses that we applied to the robot, and we evaluated if it fell or not based off of how much impulse we applied to it. And we did this several trials on each side with different amounts of mass. So the key result is it could reject a non-zero impulse on each side, and it led up to rejecting disturbances of up to 0.1 kilograms meters per second. The important metric here is not the magnitude, but in fact it was able to reject a non-zero disturbance, which allows us to conclude that it's actually passively stable and not just like marginally stable standing there like a inverted pendulum. One important thing is these magnitudes, they're kind of low, but we're looking into detecting if we're falling, and we can actually take a step out of this. So normally we don't expect too many disturbances while we're just standing there, but if we do get hit by something, we can take a step and balance ourselves. One other stability test we looked into was replicating the cadaveric study on the flamingo over on the right side, where they disturbed the body by pitching it on its front and back. And we did the same exact thing on our robot. So we were able to disturb it up to 20 degrees backwards and 15 degrees forwards. And it actually stayed at that position on the boundaries. And this is because in our motors, there's a lot of compliance and friction, and it didn't allow it to kind of go back to its equilibrium state like the flamingo does. And we're looking into making this more compliant or less compliant by using direct drive motors to let it kind of reduce the friction from the motors. One important thing is it actually walks, it doesn't just stand. We were able to get around 6 to 7 steps by hand tuning a walking gait. And in the future, we're looking into upgrading the motors from servo motors to actual direct drive motors, where we have more control over what we're actually commanding it rather than just position commands, since the servos actually abstract away some of the control. We're looking into adding IMUs or an IMU to do some stabilization while it walks, as well as we're looking into doing gait optimization through simulations. We originally did a simulation with the Simscape, or MATLAB Simscape environment, and we weren't too happy with how it dealt with context. As you can see in the beginning of the video on the right, it kind of bounces quite a bit. And we are looking into using either like Majoko or Dart or some other similar simulation environment that handles context better. In the future, we're looking to upgrade the motors in our robot, and we're looking to specifically put a direct drive motor in the hip to give some more stability in that pitch test that we were looking into. We're also looking into closing the loop on the gait cycle using like an IMU to help with stabilization. One cool thing we want to look into is instead of using springs, use some sort of tendon mechanism where we can add some transmission into the system, move the motors up, but still give that springiness to each of the joint that adds to the stabilization of our robot. We're looking into creating a simulation using one of these environments or something similar. So if you guys have any cool environments you want to share with us that would work well with our robot, we would love to hear that. And in the end, we want to kind of optimize both standing with zero energy, as well as creating an efficient walking gait, because some of the things that we added into the robot to make it stand with zero energy makes it less efficient for walking. So we want to try and see where those trade-offs happen and how we can optimize both at the same time. All right, thank you.
Got time for questions.
Hi, I'm Talia Moore, and I'm from the University of Michigan. I was wondering, so when I saw your bipedal walking gait, it reminded me a lot of a penguin because it moves its huge mass, a huge amount from side to side in order to get a really small step. And you usually see that with like really, really small, like short-legged systems. And I was wondering if you were gonna look at longer-legged systems, like actually look at the Flamingo Locomotion, and especially look at the transitions from Flamingo Locomotion to standing passively and passively standing into locomotion. I think that would be really interesting, and especially because flamingos are in these kind of like semi-aquatic places where they need to have really long stride lengths, right? And kind of get through marshes. So I think that it would be a good application. Is that something you're interested in looking at?
Sure. Yeah, it's a little weirder having two people taking the questions. Yeah, so it would be interesting to look at. I think from sort of where we're coming from as roboticists, we would be looking more to do like trajectory optimizations for that sort of thing rather than maybe directly looking at how a flamingo would be doing it. But yeah, it would definitely be interesting to look at those transitions into and out of the standing pose.
Yeah, one big thing is with our motors that we were using, we really wanted to do a quasi-static gait because we weren't sure if our motors could move fast enough or kind of catch ourselves while we're falling. And so once we kind of make those upgrades and like add additional sensors for closed loop feedback, hopefully our body movements would be minimized as well.
My name is Kate Bonin, and I'm from New York University. And my question is about, you motivated the problem with these search and rescue robots, and they're often not necessarily in a place that is flat. And so I was wondering how much the passive standing strategy is dependent on the external terrain cooperating in order to allow for the robot to be stable.
Yeah, so right now it mostly stands on flat ground, and with the more rough terrains, I think we're also going to look into like how we can find more behaviors that allow passive standing, and like looking into different designs if we need it, or if we can implement it with our same design.
I have the same question, but how does the flamingo lock its ankles and knees on not flat ground?
Are you referring to an actual flamingo?
An actual flamingo. You're copying the actual flamingo,
Okay.
which looks like it's a kinematic lock in a fixed configuration, which would only work if you knew you were on flat ground. So,
Okay. So my understanding of how the flamingo works is sort of there's a hard stop in its ankle that engages when it's leaned like a certain angle over. I would imagine that that sort of mechanism would still work whether it's flat ground or not. And then
Yeah, we think so. Also, one thing we noticed when looking at flamingos is they actually move their heads a lot. So I think they can redistribute their center of mass by changing where their head is. So we could also look into adding some sort of way to redistribute our center of mass, maybe like put our battery on like a gantry system or something like that.